Okay. All right, so now we're getting on to 6.2 is volume. Okay, so last section we talked about area, right? So basically the concept of area is like this sheet of paper is how much is this sheet of paper is involved in this entire surface, right? Or how much is it accompanying that surface. Now when it comes to volume, right, it's a three-dimensional object like a chair or a sphere or something like that. So the easiest volume you guys have seen is a cube. And as you guys know, it's very difficult to draw three-dimensional objects on paper. So we're going to try our best when it comes to solving these or graphing these so you can see what's actually happening. I don't know about a lot of you guys, but I'm a very visual learner. So I kind of have to see what's actually happening in the figure. That way I know, what's going on. So again, I'm going to try my best when it comes to the graphing, this kind of stuff. But again, mostly it's going to be these type of stuff, okay? And the biggest one I'm going to be using a lot in this section is the sphere. Okay. So now, what is a volume persist in the xy plane, right? Because xy is only two-dimensional. How do we get a three-dimensional object just from a two-dimensional plane? Now, for this one, you're going to have a little bit more of a little bit more creativity when it comes to it. So essentially, it's happening. Let's suppose we have this curve here and this curve there. Okay, and I cut it off here and I cut it off there, right? So from A to B, essentially. Now what's happening is if I rotate this around, like around itself, I just keep going this loop and a loop and a loop in this direction. What do I get is an actual surface, kind of looking like this, right? Again, just rotating it this way and that way. So I kind of get like a circle, right? You notice the circle gets rotated over here when it comes to it. Now, how we're going to find volume is in, right? We don't have completely three-dimensional objects, and we don't have to do those, double integrations you guys be doing in the later classes. We go into a higher calculus. So what we're going to do is, well, what happens if I just cut a slice of this three-dimensional object and be rotated in the xy plane? So if I just cut it like this, just cut it like that. It's a nice slice of it, right? Just a good slice. And see what we get here. So if I cut it, I actually get a disc or a circle. So if I go over here, and if I just look at the slice now, what the slice ends up being is now a complete disc or circle. Okay? And this is kind of nice because we do know how to find the area of a circle, right? That's far easier to deal with, right? So quickly just area of a circle is just pi r squared or a disc, right? It's the same process when it comes to it. And that's going to be how our method of finding these surfaces or these volumes are going to be as well. If you notice now, if we just find the area of each individual slice and add them all up, that is essentially the volume of this entire surface. Or if we just add up all the individual areas, that corresponds there. And if you notice, we already know how to do that. That's the limit, right? So essentially, the whole concept behind this stuff is we're going to take the limit as n goes to infinity of all of these areas of these circles, right, when it comes to it, or just the area itself. So the areas of each n sub n's or each individual circle when it comes to it. Now, again, we already know what that means, right? So therefore, we take the limit as of an infinite number of rectangles, or in this case, infinite number of circles, that's taking the integral of it. So essentially, we get something called the disk method. Well, your book doesn't really call it the disk method. I prefer the disk method because it identifies three major types of ways we're going to be doing this, and then that way you can see, okay, which one's easier, which one's harder, and from there on when it comes to it. Okay? So the disk method is the easiest of the three we're going to be dealing with, and that's the reason why we start off first with a disk, and then we go a little bit more complicated. Okay? But again, your book doesn't really specify this is the disk method. I just do it myself. That way, identify the three major parts of it. Your book kind of splurs it all into one itself. Okay. So the disk method says let S be a solid that lies between A and B. So in this case, this is going to be our A, and this is going to be B. Right? If the cross-sectional area of S, so what this means is if I just make a slice of cross-sectional, so in other words, perpendicular to the solid, right? So it's exactly perpendicular slice to the solid. In the plane PX, so this is technically like our P of X, if you want to call it, okay, through X, and is perpendicular to the X-axis, which is, again, perpendicular to the X-axis, is A sub X where a is a continuous function, then the volume, so this is going to be our area of this individual slice. That's as a sub x represents. Okay? So therefore, the volume of this surface, call it S, is equal to the integral from a to b of the area, or in other words, the area function in terms of x dx. Now, we just talked about this. These are all circles, or disks themselves, and we know the area of a circle is pi r squared. So essentially, we can rewrite this area equation in terms of r, and this is just the integral from a to b of pi r squared dx. So therefore, all we have to do is find the radius of this circle with respect to x, and just plug them in and find our volume. And that's called the disk method itself. Okay. So let's try an example out so you can see how this will actually be applied here. So example 1 says, find the volume of the solid obtained by rotating about the x-axis, the region under the curve y equals the cube root of x from 0 to 1. All right, so just firstly, let's see what's actually going on here. Right? So from 0 to 1, so I'll just put 1, here's 0. And again, I'm just going to graph this. So, plug in 0, we get 0. Plug in 1, we get 1. So essentially here, right? So what I'm going to do is I'm going to go down here, and I'm rotating this whole area around the x-axis. So I'm going this way. So I'm just rotating it this way around. So if I rotate it this way around, what I want to see is what solid do I get. So if I rotate this right now, that means it goes down here to -1, right? So I just rotate it around because it goes outside the page and then inside. So this goes here. So in fact, we kind of get a solid like this. Kind of like a cone shape. So again, it just rotates this way. So hopefully that's a little understanding when it comes to that. I know whenever I was in this class, it was really hard for me to understand what it means by rotating. Because again, I'm a visual learner, so I have to see what's actually happening itself. So this whole thing is being rotated. So if I just color this, so this whole chunk here is the solid itself, and it kind of looks like a cone being rotated itself, or a top. If that's easier, right? So if you do it this way, here is our top, and that's this, the floor itself. So we kind of want to find the volume of this top we just created using this curve and rotating it around the x-axis itself. Okay. Now, when it comes to the disk method, right? So whatever we're rotating, that's how your disk is going to be. So therefore, our disk is going to be rotated this way. So it's actually going to be there. So there's our disk we're rotating. Okay? That's why it's called the disk method, or our circle we're going to be cutting and finding the integral of. Okay? So we know the area, or in this case our volume, is integral from, in this case, 0 to 1 of pi r squared dx. Now the only thing we got to figure out is what's our radius, or in other words, the radius of this circle here. Remember, the radius is from the center up to any point on the circle. So if it's easier, we just want to find that distance here. Well, that's easy, right? That's the same thing we did earlier today. It's just integration. So it's top minus bottom. So this is the top, so this is y. This is the cube root of x minus, and where did we stop is 0, right? Because that's exactly the line y equals 0. So that's just the cube root of x. So that is our radius. So now we plug it in and we can find our volume of this solid. And I'm going to rewrite this into its exponential form just to make it easier to look at. And I'll bring this out when it comes to it. So our volume is going to equal to pi, and this is x to the integral of 0 to 1 of x to the 2/3 dx. And now notice this is a very nice integral, right? It's just not power rule. So adding 1, that gives you 5 over 3. So x to the 5/3 Yeah, 5/3. And doing this one, this should be 3 over 5 here. And we evaluate this at 1 and 0. So plug it in. 1 to any power is just 1. So this is 3 pi over 5. And plug in 0, we get 0. So our volume is 3 pi over 5. Okay, so unfortunately, it's not always going to be that simple just be rotating around the x. What if we want to rotate this now around the y, this way now? Instead of going in and out of the paper, it's going the other way, rotating going this way. And that's what we're going to talk about in example 2. So example 2 says, find the volume of the solid by rotating the region bounded by y equals x squared, y equals 4, and x equals 0 around the y-axis. So again, let's see what the heck's going on so we can see what's actually happening. So first off, let's just graph a region. So, and we want it from x equals 0 to y equals 4. 4. So we plug in 0, we get 0. Plug in 1, we get 1. Plug in 2, we get 4. So there's our portion. So if I rotate this now, just like kind of like this one, so if I rotate this way, notice it's going to be mimicry on the other side, right? So it's basically the same parabola on the other side. So I'm rotating it this way. And again, I also end up getting another top. So now the only difference is the top is now on the y-axis instead of the x-axis being on the side.